Welcome to Origin Stories, where we explore the surprising beginnings behind the materials, tools, and ideas that shape our everyday lives. Today, we're diving into the creation of something so common, so familiar that you probably touched it today without a second thought. Stainless steel. It's in your kitchen sink, your cutlery, elevators, medical tools. It supports bridges, fills skyscrapers, and protects ships. Strong, sleek, and famously resistant to rust, it's one of the most important materials in the modern world. But where did it come from, and how is it made? The story begins deep underground with a rock. Stainless steel starts with iron ore, a mineral pulled from the earth rich in iron oxides. This ore has to be transformed, refined, purified, and strengthened before it becomes anything close to stainless steel. That transformation begins inside a blast furnace where the iron ore is melted down with coke, a high-carbon fuel, and limestone. The intense heat, over 1700 degrees Celsius, breaks the chemical bonds. The carbon from the coke combines with the oxygen in the ore, releasing carbon dioxide and leaving behind molten iron, often called pig iron. Pig iron is strong, but it's brittle and prone to rust. That's where things get interesting. To make stainless steel, we need something more. We need chromium. In the early 20th century, researchers discovered something remarkable. When a certain amount of chromium was added to steel, around 10.5% or more, it formed a protective layer on the surface, not a coating, a reaction. The chromium reacts with oxygen in the air to form a layer of chromium oxide, so thin it's invisible, yet so strong it stops rust in its tracks. This discovery turned steel from an industrial workhorse into a technological marvel. Suddenly, we had a material that was not only strong, but clean, beautiful, and nearly immune to corrosion. So, how do we transform raw molten iron, fresh from the blast furnace, into the versatile and corrosion-resistant marvel we know as stainless steel? It's a fascinating process involving careful alloying and precise control. The first crucial step is introducing chromium. This is usually done by adding ferrochrome, a pre-made alloy of chromium and iron, directly into the molten iron. As the ferrochrome melts and mixes, the iron begins its transformation into an alloy. But the journey doesn't end there. To achieve the specific properties required for different applications, other metals are carefully introduced into the mix. The composition is tailored to the intended use. Nickel is a very common addition to the recipe. It significantly boosts the steel's resistance to corrosion, preventing rust and degradation. Plus, it imparts a beautiful, shinier and more polished finish, enhancing its aesthetic appeal. For applications in harsh environments, molybdenum is often added. This element dramatically improves the steel's resistance to the corrosive effects of salt water and acidic substances, making it ideal for marine equipment or chemical processing plants. And for applications where strength and durability are paramount, manganese is the go-to additive. It enhances the steel's overall strength and its resistance to wear and tear, ensuring a long service life. The key to creating the perfect stainless steel lies in precision. These metals aren't just thrown in haphazardly. They are meticulously measured and added in precise, predetermined amounts. Even the slightest imbalance in the alloy's composition can have a significant impact, altering the steel's final characteristics and performance. This isn't just about melting metal together, it's a sophisticated process rooted in metallurgical science, requiring expertise and careful control at every stage. Once the elements are added, the molten steel has to be refined, and that means removing impurities like excess carbon, sulfur, or unwanted gases. This is where argon-oxygen decarburization, or AOD, comes in. Argon and oxygen gases are injected directly into the molten steel. The oxygen burns off carbon and impurities, while the argon controls the temperature and protects the chromium from oxidizing. The result is a cleaner, more stable alloy, ready to be shaped into something solid. Next, the purified liquid steel is cast, poured into molds that are rapidly cooled. This process is called continuous casting, and it transforms the glowing liquid into long, solid slabs or billets. But the story doesn't end here. After the initial casting, the journey of steel continues with hot rolling. This is a crucial step where the steel slabs are reheated to an extremely high temperature. Then they're passed through a series of heavy, powerful rollers. These rollers act like giant presses, compressing and stretching the steel. This hot rolling process is more than just shaping. It fundamentally refines the steel's internal structure, aligning its grain for enhanced strength and durability. It's also where the steel begins to take on its intended form, whether it's destined to become flat sheets for car bodies, thick plates for construction, cylindrical rods for machinery, or coiled wires for countless applications. The possibilities are endless, however. Even after the intense heat and pressure of hot rolling, the steel's surface isn't quite ready for prime time. It's typically rough, often covered in a layer of oxidation known as mill scale. This layer, along with other surface imperfections, needs to be thoroughly cleaned before further processing can occur. This is where pickling comes in, a vital step in preparing the steel for its final application. The steel is carefully submerged in an acid bath. This bath usually contains a potent mixture of hydrochloric or nitric acid, carefully formulated to aggressively strip away surface impurities and that stubborn oxidation layer. As the steel soaks, you can witness the transformation, revealing the smooth, clean and pristine steel underneath. From here, depending on the desired properties and application, the steel might undergo cold rolling. This is a room temperature process where the steel is passed through precision rollers, allowing for extremely accurate control over its final thickness and resulting in an even smoother surface finish. To further refine its properties, the steel may also be annealed. Annealing involves a carefully controlled reheating process designed to relieve internal stresses within the metal. This makes the steel more ductile and easier to work with in subsequent manufacturing processes. Finally, the steel goes through finishing. This is the stage where the steel's final appearance and surface characteristics are determined, tailoring it to its specific end-use requirements. Some steel is meticulously polished to achieve a mirror shine, perfect for decorative applications. Other steel is brushed to create a matte effect, reducing glare and providing a more subtle aesthetic. Still, others might be given specific textures, not only for aesthetic appeal, but also to enhance functionality, such as improving grip or providing a surface for coatings to adhere to. Before any batch is cleared for shipping and makes its way into the world, it undergoes rigorous quality control. This isn't just a formality, it's a critical step to ensure that every piece of steel meets the required specifications. Samples are meticulously analyzed for their precise chemical composition. We're talking about identifying and quantifying every element present, ensuring the steel matches the intended alloy. The steel's strength is then put to the test. Sophisticated machines apply controlled forces, measuring its tensile strength, yield strength, and resistance to deformation. Beyond bulk properties, microscopic structures are carefully examined. This reveals the grain structure, the arrangement of crystals within the metal, which significantly impacts its overall performance. The goal is simple yet paramount: to eliminate surprises. Only steel that precisely meets the required standards is approved and sent on its way, destined to become the objects and structures we depend on daily. Take a moment to really consider that. That stainless steel fork resting on your dinner table, it represents the culmination of high-heat chemistry, incredibly precise engineering, and over a century of relentless scientific progress and refinement. From its humble beginnings as raw iron ore to its transformation into a gleaming, polished finish, stainless steel is a material that was born from necessity, but has been perfected through constant innovation and improvement. And the story of stainless steel is far from over. It's a narrative that's still actively being written. Researchers and metallurgists are developing new alloys every single year, pushing the boundaries of what's possible. Stronger, lighter, and more sustainable variations continue to emerge, ensuring that stainless steel remains at the very heart of our ever-evolving world, shaping our future in countless ways. So, the next time you open your fridge, turn on your faucet, or ride in an elevator, take a moment to consider the journey of the steel beneath your fingertips. It's more than metal. It's the story of discovery, chemistry, and craftsmanship, woven into our daily lives. Thanks for watching Origin Stories. Be sure to subscribe and stick around. We've got more unexpected backstories behind the most ordinary things, because everything has an origin, even the stainless steel in your spoon.